Okay, let's look at an example here of doing, we'll do a node voltage problem, but kind of focusing on how to put it in matrix form and solve that with our calculator. And so we have a circuit here. When we start off with a circuit, we need to do node voltages. We'll need to define a reference point. So let's just pick this corner here. It's good to pick the negative of a voltage source is often a good place. And then we need to identify our nodes. And so we'll have several nodes. So this is one node here, so we're not going to name that anything different. That's the ground node, so it doesn't need a separate name. But let's just call this node 1. So we'll have V1, that's a voltage, V1 at node 1. So it's plus here, minus at ground, right? Well, let's name this node 2. So we'll have V2 here. V2 is plus here, minus at ground. Continuing on, we have a connection point here. We'll call this node 3. So we'll have V3 up here. Again, plus here, minus at ground. And then we have a node 4 here. Plus up there, minus here. Okay, and so probably we'll go ahead and write it this way. Write the equations this way and then put it in matrix form. So in theory then, if we have 4 different nodes besides the ground node, we will have 4 different equations because we'll have 4 voltages that we need to calculate and 4 equations that we need to write. The reason I hesitate is that the way I've made this one, it's hopefully clear that V4 has to be 5 volts, right? And so that equation is basically there and it's solved, so we really could just write equations for these 3 and solve those because V4 is already known. And so that's one advantage of making the voltage source. It's kind of like a super node with the ground kind of idea. So let's just leave that one as, should we leave it as solved? Let's just leave it as an equation and we'll do a 4x4 example just for fun. Okay, so for the node voltage method, right, we've defined our ground, we've defined our nodes, and then we're going to write KCL for the different nodes. So let's do KCL at node 1. Node 1. Okay. And so node 1 is here. So we do KCL, we can just add up all the currents leaving the node is what we like to do. And so it's easy, or we could do current in equals current out, either whichever we want to do. But here's node 1, right? It only has 2 things connected to it, the 20 ohm resistor and the 2 amp current source, right? We know it's a current source because it has an arrow, and so it's defining a current. And so let's just do KCL as adding up the currents going out. And so this current is 2 amps is going out, so it's a plus 2. It's going out. And then the current going out for this resistor, we have plus voltage here, minus voltage here. And so the current goes, positive sign convention, calculating this current. So hopefully remember the method. It's just going to be V1 over the resistance over 20. So V1 minus 0, because it's V1 minus ground. So it's just V1 over 0, and that's all we've got, so that equals 0. Okay? And so if we want to write this in the standard form for putting it in a matrix later, we want something, all the things multiplying voltages on one side and all the constants on the other. So we would let's just write it all out. So we'll have 1/20th V1 plus 0 V2 plus 0 V3 plus 0 V4 equals -2. All right, so that's the equation here. These are kind of pointless to write, but when we're putting it in the matrix, anyway, I want you to see how they go into the matrix with that. You don't have to enter zeros in the matrix. So let's do KCL at node 2. So node 2 again is a simple one. It only has 2 connections. So it has the current from this source now is going into the node. So the current leaving the node here is -2 amps. Right, because it's not because it's actually entering, so it's negative. And then the current going this way from V2 to V3, remember we take V2 minus V3, the voltage plus here minus there, divided by the resistance of the branch, so 10 ohms. And that is all there is, so that equals 0. So again, we can write it in the form to put in the matrix. We're going to have a 0 V1, no V1s in this equation, plus 1/10 V2 And then we're going to have a minus 1/10 coefficient on the V3. No V4, so 0 V4. And then the 2 comes the other side is positive now, and so equals 2. All right, continuing on, KCL at node 3. Node 3 has 3 things, all right, 3 branches connected to it, 3 different places where current can go. And so we're going to have 3 terms. So the current leaving, let's just do the source first. So the source current is leaving node 3, so it'll be positive. So we'll have plus 1. And then we'll go this way first. So going from here to here, we're going to have V3 minus V2. The thing connecting 2 to 3 is 10 ohms. So we'll put plus over divided by 10. And then the current going that way is going to be V3 minus V4 over the 5 ohms, and that's all there is, so that equals 0. All right, so writing this in the standardized form, again, we have no V1, so 0 V1 plus coefficients of negative 2 are just this negative 1/10 V2. For V3, we've got 2 things. We've got 1/10 and 1/5, multiplying V3, and then V4 is just a negative 1/5, and then the 1 amp goes to the other side and becomes negative. So again, negative 1 for their constant term. Okay, so now we've got 3 equations, and now we could go to node 4, but we can't write equation like a current node equation, so I guess we'll call it super node for 0, something like that. So we would write equation like this, but we've got since it's part of the ground node, basically all we need to do is look at its defining equation here. And so for this supernode, then we would just say V4 equals 5 volts, or V4 minus 0 equals 5 volts. So V4 equals 5 volts. And so I guess the whole equation is 0 V1, 0 V2, 0 V3, 1 V4 equals 5. Okay, so now that I've written them all out this kind of long way, we can put them in the matrix easily, right? So we're going to make a matrix. It's going to be 4 by 4, and it's going to be multiplying all the voltages, V1, V2, V3, V4, and it's going to be equal to the constants on the other side of the equation. All right, and so when we multiply vectors and matrices, we multiply the row times the column, right? So let's put in the number. So this will be 1 over 20, a bunch of zeros, 0, 0, 0. So, and that equals negative 2. So if we would just undo this with our matrix multiplication, we'd say this coefficient, 1 over 20 times V1, plus this one times its corresponding coefficient down the column. So 0 times V2, and keep moving, 0 times V3, 0 times V4. It's kind of a boring example. Okay, that's this side equals the corresponding element in the row on the other side, negative 2. So that's the equation we started with up here, right? So matrix math is row, element by element of the row gets multiplied by element of the column, gets back into an equation, equals whatever's on the other side. Okay, so let's just plug the rest of these in. So this one is a 0 V1, 1/10 V2, negative 1/10 of times V3, and a 0 times V4, and we get a 2 on the other side. And then we've got 0, negative 1/10. This is 1/5 is 2/10, right? So we got 3/10, and then negative 1/5, and that equals negative 1. And then finally we got 0, 0, 0, 1, 5. Okay, so this is kind of in matrix form. Again, we could take each row times the column of V elements, and we get its corresponding equation back. All right, hopefully you see that. So let's just write this in matrix form. So some matrix C times the vector V equals some constant. Let's just call it, I don't know what they are. Let's just call them D. I don't know. And so if we want to solve this, we can't divide. So to solve this mathematically, we wanted to solve for V, we just divide by C, but we can't divide by matrices. With matrices, we multiply by the inverse. All right, so we're going to left multiply by the inverse. And so on this side, I'm going to left multiply by the inverse times D. All right, maybe I shouldn't have done that shorthand notation. But anyway, we start with C times V equals D. All right, and so we're going to multiply both sides by C inverse. And so C inverse times C, this is like C divided by C. Right, just becomes identity matrix, like a 1. Anything multiplying by a 1 or by the identity matrix is just that thing left. So we're just going to have the voltage vector left, and that's going to be C inverse times D. All right, and so in our calculator, when we want to solve for the voltages, or if we were doing the mesh method and we had a vector of currents, whatever this is, we could just, basically we're just going to have, it's a set of linear equations, and we can just do an inverse to get the answer. And so in our matrix, we're going to want to take this, or in our calculator, we're going to take this whole matrix and then take its inverse and then multiply by this D, -2 to -1, 5. I guess I'll put these in here just for example. It's just the same matrix back, and we're just putting a little inverse up here to show where it's like dividing by a matrix, but we can't do that, taking the inverse. And so we put this in our calculator, and we'll get an answer, and that will be our V vector. V is equal to C inverse D. And so the top element will be V1, then V2, V3, V4. So computers and calculators are good at doing repetitive things, and so the nice thing about knowing vector math is we can kind of do one equation with a bunch of pieces in it, and solve a whole bunch of equations at once. So a lot easier than doing a whole bunch of algebra on these. So for this calculator, if you have a different kind of calculator, it would probably be worth your time to figure out how to do it on your calculator, but somehow you got to enter a matrix. So figure out how to enter a matrix. And this one, you go to the menu, you go to the matrix vector menu. So I'm just going to hit a 7. You could go down with the buttons, but just if you hit 7, it chooses that one. And then I want to create a matrix. So I'm going to do 1. And then I want to create a matrix, so I'm going to do 1 again. All right, so now it's asking me how many rows and how many columns. In this case, I've got a 4x4, so I'm going to type 4. And I got to get over here. Maybe I'm not sure if there's a better way, but anyway, get over here to do another 4. So I've got 4 rows and 4 columns. All right, and this to take an inverse, you have to have the same number of rows as you have columns. So we're there, and that's the same. When you want to solve a set of equations or find 4 variables, you have to have 4 equations. So that's where that kind of comes from. So let's hit OK. So now we've got an empty matrix. So let's do 1 divided by 20, 0, lots of zeros. -1/10, 1/10. However you have to get them into your calculator, get them in carefully. Oops. All right, and so I've got the matrix entered, but we don't want just the matrix multiplied by this. We want the inverse of the matrix. All right, so on mine, it's got this little caret symbol, this little to the power of. So I'm going to raise it to the power of -1 is the inverse. I've got an inverse function to the -1 power anyway, -1 power. Let's get out of that, and then we're going to take that times the vector. So we got to create a matrix again. So menu, matrix, create, and this time it's got 4 rows but only 1 column. So we're going to do 4, 1. Right? 1 column matrix or a vector, right? So then we just put these in -2, 2, -1, 5. Okay, so we've got our C inverse times D, and so when I hit enter, I should get a vector that is our vector of voltages. And so there's our vector of voltages. Looks like, anyway, this is just a made-up problem, so not anything realistic about it, but we get -40, so my first voltage, or V1 is negative with respect to ground. It's lower than ground, right? 40 volts, but that's okay. -40 volts, 20 volts, 0 volts. What? 5 volts. Which V3 is 0. That's kind of strange. And so this, it's like this current source is shorted out. No voltage across it, no power. Again, danger of just making up a problem. All right, well, so hopefully you see the method. Let's see, let's just kind of double check. Well, we do see that V4 is 5 volts, so that is good. We knew that it had to be. V1 is -40 volts. So if V1 is -40, the current is actually going this way, right? And it's 40 over 2, so we got 2 amps going this way, right? Because V over R would be 2 amps going that way. And that agrees with the 2 amps here. Yes, of course, there's 2 amps going that way. And so then this one, this is an easy problem to solve since I did the current sources like that. We didn't have to do all this matrix stuff. But anyway, so we got 2 amps going that way, so that agrees with the -40 here, and we got 2 amps going this way, and so V2 and V3 have to be V2 minus V3 has to be 20 volts also. V2 minus V3, yeah, okay. All right, so it's kind of a strange problem. You wouldn't build something like this in real life, but hopefully it gives you an idea of how to do the matrix method and a little bit of practice with node voltages.